So first, I wanted to thank you for your interest and the time you take today to see in more detail the JKSimMet software capabilities. So welcome to the first of a series of webinar sessions where we will be showing the JKSimMet features, capabilities, enhancements, and updates. Also tricks to get new users more familiar with the software, and also to keep current users up to date on the new features and new additions to the software. So my name is Percy Madrid. I'm a communication consultant at JK Tech. I work in the Mind Process Solutions group at JK Tech for 8 years now. So I'm often involved with process integration projects such as Mind to Mill or Mind to Concentrate. Certainly more focused these days on entire mind value chain optimization projects. Apart from consulting, my role also involves the delivery of JKSimMet training courses and provide technical assistance to JKSimMet users worldwide. So today's presentation is JKSimMet at a glance. So it's going to be a quick review of the software and its capabilities. So this will probably take around 30 or 40 minutes, after which I will take some questions that you might have. So the recommendation is to put your questions in writing as I go through the presentation. So I just enable the chat for you. This will hopefully help save my time and keep more fluent communication. So I hope you all see the screens I have. So I just changed to the next slide. So hopefully you all see the new slide. So this is to quickly show you where the software JKSimMet comes from. At the University of Queensland, there is a Sustainable Minerals Institute that comprises 6 different research centers covering the entire mine value chain. So you can see the 6 of them listed from left to right. The second of them is the Minerals Processing Research Center, Julius Kruschnitt. So all these centers do research funded by the mining industry of Australia and overseas. So some students, postgraduate students, or many of them international students that come to Australia to do their postgraduate degrees on various fields of the mine value chain. So JK Tech is a technology transfer company that commercializes the outcome from the research back to the industry. So only at this second research center, JKMRC, more than 40 years of research and more than 200 theses have led to the development of mathematical models of the various pieces of equipment commonly used in combination circuits. So these include crushers, screens, ball mills, side mills, hydrocyclones, HPGRs, and some others. So these models are now available in a single platform that we call the software JKSimMet. So what can JKSimMet do? So for example, in the software, we can represent a single piece of equipment or the whole combination circuit. Say for the purpose of this exercise, or just to show you the concept, if we have, say, a piece of equipment or a combination circuit in the plant, we represent that with mathematical models in the software. So these are mathematical models, say, for example, a hydrocyclone. I like using the hydrocyclone as an example because it has 2 product streams. So if this hydrocyclone is fed with a certain feed rate, feed density, and particle size distribution, so obviously it's performing in such a way that it's producing two product streams with a certain flow rate, density, and particle size distribution for each product streams. So this is how the circuit is performing, or the particular piece of equipment is performing. So once the models are calibrated, then we can use the models to predict the process or equipment performance in terms of particle size distribution, solids tons per hour, and percent solids. So the models will just predict the performance. Say, if this cyclone, we have developed a model for this cyclone, and then we can use the model to predict the effect of given changes on performance, then we can, for instance, predict, or the model can predict the performance. And the type of changes that you can make on the simulations include the all characteristics, equipment dimensions, and operating conditions like uh, feed density, number of hydrocyclones, for instance. So all of these type of changes that I highlighted in red have an effect on equipment performance, and the models will be capable of predicting that with a reasonable accuracy. So this is basically what the JKSimMet software does. Uses mathematical models to predict performance. Performance in terms of size distributions, solids tons per hour, and percent solids, as a function of all characteristics, equipment dimensions, and operating conditions. So how does JKSimMet do it? So if we have a piece of equipment or a combination circuit, then we can represent those in the software with models. Say this yellow box we see in the screen is a model representing a piece of equipment or a combination circuit. Obviously, if it's a mathematical model, it requires some data entry, some input. So this type of input includes the feed size distribution, or feed rate and feed density. So that needs to be the input to the model, but we also need other information like equipment dimensions for mills, for hydrocyclones, or for crushers. Also, we need to input operating conditions such as water additions, boil loads, mill speeds, number of hydrocyclones. But there is other input that we call model parameters. They are of two types. So we have those or specific, coming from the ore characterization tests on the ore feeding this equipment or process or circuit, and those matching specific that are estimated based on model fitting techniques. Once the model has all this information, using a model fitting technique, we can calibrate the model, and the model will be then able to predict the output. Once it has all this information, all that input, then the model is able to predict the product in terms of feed rate or solids tons per hour, percent solids, particle size distributions, mill powers, crusher powers, hydrocyclone pressure, those things. Obviously, if we are talking about combination circuit, then we are not predicting only the final product stream, but all intermediate streams actually. So this works for every single piece of equipment. So JKSimMet is a simulator software package for combination circuit, combination and classification circuits, and uses modeling and simulation. So modeling and simulation have shown to be the most cost-effective method to optimize or design combination circuits. You can always so pilot testing can be effective but expensive in the long term. Whereas with the modeling and simulation, you have the ability of conducting what-if simulations, which allow users to have a well-founded basis for their decision making without testing changes on the real plan, which might be detrimental for the operation and productivity. So there are two major things that we can do with JKSimMet. We can optimize existing combination circuits, or we can design new combination circuits. So the path to follow when optimizing an existing combination circuit is as follows, as you can see in the screen. So we first need to measure, which means conducting a survey. We then analyze the data that we collected, which includes running a mass balance. And then we do model development, and then we calibrate the model, and then we use the model to predict performance for any changes that we want to simulate. And then hopefully we come up with some scenarios that we like, that the model suggests will make the plan to perform better. So we will want to implement those on the real plant. So we can do that and then measure again to confirm whether the circuit is responding as the model predicted. So this is a continuous improvement cycle that we recommend to follow. The other major use for the JKSimMet software is when it comes to design new combination circuits. Obviously, the plant doesn't exist yet, so we are not allowed to conduct any survey or analyze any data, but somehow we should be able to develop the model. So we basically use a database where we borrow machine-specific model parameters coming from similar pieces of equipment, performing similar duties on similar ore types, and use those suitable and selected model parameters and run simulations. And obviously, the implementation will come with the plant construction. Okay, so how models work when doing one or the other major function, when designing or when optimizing combination circuits. For example, when we optimize combination circuits, the circuit exists, the circuit is there, so we can measure everything. If we are able to measure everything using model fitting techniques or model calibration techniques, we can identify or estimate the machine-specific model parameters that will be fixed values for the piece of equipment. So they will be part of the mathematical equations. So the models will predict equipment or circuit performance for the particular application. And then we run simulations. But when it comes to design new combination circuits, basically we don't have the plant, we don't have all the data, we cannot collect experimental data, so somehow we need to get all this information. Once we manage to get all this information, it's just a matter of using the models and run simulations and play with equipment dimensions until we meet all the target throughput, all the typical circulating loads, and the final or the target final product size as well. I will show you, this was a bit of introduction. I will just show you now the software itself. I'm switching my screen to the software application, which you should see now. So this is how the software looks like. I will do a zoom for the circuit, which is quite simple circuit to fit in the full screen. So this is a traditional cyclone bonus circuit. Okay, I can start showing you the library. I'm just extending all these libraries so you can see that. So this library of pieces of equipment used in combination include all the ones that you see, and there are mathematical models developed at the JKMRC that are associated to these pieces of equipment. So in some cases, we have multiple models that we can use depending on the application. You can see, for example, some flotation cells under the separators folder here. However, JKSimMet is not a flotation software package. It only simulates combination circuits, crushing, grinding, classification. The only one reason the flotation cell is in there is because we can run mass balances around flotation circuits as well. So just to show you a bit of this, up here we have 3 bottoms that represent the 3 major functions that JKSimMet has. The first one is a mass balancing. The second one is a model calibration or model fitting, and the third one is the simulation. So this is the traditional exercises that we developed during a standard 5-day training course that we do. Then, for example, this is where we run a mass balance. So this is an existing circuit. We conducted a survey, we collected samples, we determined size distributions for each stream. We measure solid tons per hour only in the fresh feed stream, because that's the only one where it is available. And then we also measure percent solids on the available slurry samples. With that data, we actually populated the software with that data. So we have a platform. I just opened this window. This is what we call survey data. So this is the experimental data or measured data that we need to enter to the software. So this can be done automatically, copy across from Excel, for instance, where we enter size distributions, solid tons per hour where available, and the percent solids as well. And then we just transfer those to the actual streams, assign standard deviations, but that's part of the procedure that we follow. But I just wanted to show you. So this is a mass balance window where we are running a mass balance, and then this is the parity graph, experimental versus balance data. So this is how data is adjusted to minimize the error, to make the whole experimental data set self-consistent, where numbers add up. For example, I can also run that mass balance and see and plot the size distributions. So in this window here, you will see all the 5 streams in the circuit, and then I just set up the sizing, the size distributions for each. I'm showing experimental against mass balance data. For example, these are the 4 size distributions for the 4 streams in the circuit. And you can see dots and lines. So dots represent experimental or measured size distributions, and the lines are representing the mass balance size distribution. So it looks like there is a very good agreement between experimental and mass balance, and that is because of the very good data quality as well. Another thing I wanted to show you with mass balancing is that in JKSimMet we can do a side-by-side mass balances. So that is a 2-dimensional mass balance. So we don't focus only on size distributions, but also elements by size distribution, or a size by size. Say, for example, in this feed stream, we have a size per size fraction for the first element, and then for some other elements as well. So say iron or lead zinc, we customize that as required. That was to show you a little bit about the mass balancing part of the software, and I also have I can also show you how the 2-dimensional mass balance works. For example, if I go to this other exercise, again, this is a single hydrocycle, and I have, say, if I show you the cyclone overflow stream. I have a size distribution for the overflow, but also have assays per the stream and assay by elements. So I have assay by size for the first element, and also for a second and a third number of elements on every single stream. And then I ran a mass balance after assigning standard deviations, which is part of the procedure. And then I run the mass balance, and then I can zoom in the parity graph to see how much the experimental data had to be adjusted to make the whole data set self-consistent where numbers add up, especially because this is a classifier, so mass is conserved per size fraction. And then we can, for instance, also plot, say, cyclone feed, cyclone overflow, cyclone underflow, experimental unbalance, cumulative percent passing, and then I have the size distributions there, which indicates that the data quality was pretty good. Okay, so that was all about mass balancing to get self-consistency in the data. But once we get this, we can develop the model. We can have, for example, hydrocyclone model. For example, this one here, I just changed the exercise. Say this is a hydrocyclone. So it's set up now. It's a model. I will show you what I showed you in the PowerPoint presentation, how the model works. For instance, at the moment, so if I run a simulation, nothing happens because this is the starting point. At the moment, the model is calibrated. You see info blocks next to each stream showing key variables like tons per hour, solids tons per hour, and PAT. At the moment, I will make any change and I will see the effect of those on performance. Say I can change things like, okay, so the percent solids feeding the hydrocyclone at the moment is 62.3%. If I want to make it 60%, add more water, then what the effect would be. So since I already have a model that is calibrated, I just change that to 60 and then run the simulation. So as you can see, only on the second column of the info blocks, you will see the change in terms of the PA and the solid tons per hour. So the starting point is in the left, and on the right hand side, you have the model. So you see that because of that addition in water, cyclone pressure went up from 85 to 94. Now we are cutting finer. P80 in the overflow went from 34 microns down to 29.6. Also, since we are cutting finer, tons per hour in the cyclone overflow went down. So this is the type of thing that we can get predicted by the software. And it's not just the P80 prediction, it's the entire size distribution. So the info block is only showing a single point of the distribution. So it's actually predicting the whole size distribution that we can also plot and see. So this is the way how we use models to predict performance. We can also change things related to, say, here in this window, I open, this is the hydrocyclone model window. So this is where we enter, as part of the model calibration, the equipment dimensions. So I have the ability to change those and see the effect on the performance. For example, so I can go back on the percent solids like that, and I run a simulation. So I just went back to the original percent solids. So you can see numbers are the same in both columns of each info block, which means this is a starting point again. So I will run now another simulation, just changing, say, spigot diameter. So at the moment I have 0.021 meters. So I will go, for instance, a bit bigger depending on what's available from the cyclone manufacturer, say 0.024 or 23, and then I just make that change and run the simulation. So there is difference in the PAT, you can see, and also slightly different in the underflow PAT as well. Cyclone pressure remains constant only because the model is predicting cyclone performance in open circuit, as you can see now. So once we try this change in a closed circuit with a ball mill, then that will make an effect. Since we have more tons in the underflow, then that will in turn increase cyclone pressure. Okay, so there is one more thing about simulations that I want to show you, how we can optimize combination circuits. So that is what we call simulation manager. So this is another exercise. Again, this is ball mill cyclone circuit. The model is already calibrated. You can see info blocks next to the streams showing key stream data, including solid tons per hour and PAT. On the first column of each info block, you have starting point values. And on the second column, on the right-hand side of each info block, you have simulated values. At the moment, they are exactly the same because this is the starting point. If I start making changes, then I will see a difference. For example, in the spigot, I can go to the hydrocyclone. The spigot diameter is 0.91. If I make it 0.2 and run a simulation, there you go. Now I see a difference in performance. So say final product size went down from 0.273 down to 0.264. Because of that, we are cutting actually finer. So circulating load increased, and as a consequence, cyclone pressure increased because now we are predicting the same change but in closed circuit. So this is the type of thing we get from the software. We actually predict circuit performance as a function of the changes that we make. Okay, so I will just go back to normal on this pickup, say 1.91, like that. So I will just run a simulation, and then again back to the starting point. Now I want to show you how we use the simulation manager to run a number of simulations in a single step. For example, we found this, users find this very useful. For example, down here you have, I need to close the simulation window first. Okay, there is an option here that says simulation manager. So this is where I can set up, say, a new scenario. This scenario is gonna be called, say, 3 times spigot times 3 vortex finder times 3 cyclone feed density, like that. So just to show you how it works, say I just want to select the vortex finder, this spigot, add one more column here, and then select the hydrocyclone again, operating conditions, and this time vortex finder. And then, for instance, we'll add one more column to say select water feeder, and the required percent solids. So at the moment, the base case has this combination for vortex finder, for spigot, and for cyclone fit density. What I want to do is to try one up and one down, one step up and one step down for each, and then try all combinations. So that will give me 3 times 3 times 3, 27. I have 1, so I need to add another 26, which I can do relatively quick. How can I do this? Sorry. Okay, I'll just time here again. 27 combinations. I'll do it quickly. Okay, so I have those, and then I have something similar. Okay, there you go. I will quickly select cyclone spigot, and then the cyclone vortex finder, and then the water feeder require percent solid. So at the moment, we have this for the base case combination. So I will add other 26 simulations like that, and then say I want to try one up and one down for spigot, say 0.18 and for instance 0.2. Say one up and one down for the same vortex finder. So this is going to take 1 minute, and then I will try the same combination but for one down, which is probably 3, 4. Like that, and all of this is for 60%. And then I can try the same of these combinations down here, but for one down, which is for instance for one up on vortex finder, which will be 0.365 for instance. And all for this percent solids for the same percent solids. So I can take this block of 9 and paste it here, but now say for 59 or for 60% solids, one down, all of them are 60. And then I take this block of 9 again, list of combinations for percent solids of, say, 60, 60.9, for instance, 62. Okay, so we have all those 27 combinations, including the base case. So combinations of 3 cyclone spigot, 3 cyclone vortex finder, and 3 different cyclone fit densities. So I want to simulate those 27 scenarios. So I want to see the results. I mean, in terms of streams, I want to choose cyclone overflow and select the PAT value, because each combination is going to give me a different final product size. I want to see which is the PAT value for each. Then I want to see the result in terms of cyclone underflow, percent solids, because, well, because the percent solids is going to give me an indication on how close we are to roping conditions, for instance. So this is a number that doesn't really mean percent solids, but it will be updated once we run the simulations. Then we add one more for cyclone underflow again, but this time for solids tons per hour, because that is going to give us an indication of circulating load for each combination. But we also want to see the results for those 27 combinations in terms of the cyclone pressure. So we go to the hydrocyclone, select performance data and cyclone pressure. We need calculated pressure for each. The base case is 90 kilopascals. And there is one more thing I want to see the results. I want to see the results in terms of water split to overflow, because predicted water split to the overflow is an indication of how efficient the classification is. So for those 27 combinations, spigot, vortex finder diameter, and cyclone fit density, I will get predictions for each of them in terms of cyclone overflow PAT, cyclone underflow percent solids, cyclone underflow solids tons per hour, and cyclone pressure, and also water split to overflow. So it's actually to overflow. Yes. Okay, so once we set up that, we are ready to go and simulate them all in a single, all simulation conducted. So those 27 combinations were simulated in a single step. So we get values for P80, cyclone overflow P80 for each combination, cyclone underflow percent solids. So that gives us an indication of how close we are to roping conditions for any given combination. And cyclone underflow is an indication of circulating load. And also we get performance data, cyclone pressure for each case. So we have more or less pressure, but also water split for each combination, which is an indication of efficiency, cyclone efficiency, classification efficiency. So with this data, I can just copy that across to Excel and then analyze the data over there and come up with the scenario that is optimal for my purposes. So this is a quick explanation on how we use models to simulate, and then how we get the simulation results, and we can potentially use that to decide which way to go. So I also wanted to show you more complex combination circuits with JKSimMet. So now you should have this more complex circuit in JKSimMet on your screen. I'll do that. So this is a large combination circuit consisting of SABC, but with pre-crushing, so 3 different pre-crushing plants. So we can get to develop mathematical models in JKSimMet for circuits that look more complex than the ones you originally saw. So, and then each of the pieces of equipment have the some mathematical models associated to them. So this is basically how we use JKSimMet to predict circuit performance. I'll just go back to so it's very important that when we use JKSimMet, either for optimization or design, that we follow the method, the right method. That for optimization includes the path that you see on the left. So the accuracy of the predictions will basically depend on 2 things. Number one is how good the data quality we use to develop the models are. Second thing, and very important, is how far we extrapolate from the baseline. So the farther we extrapolate, we might be, the less accurate the predictions will be, we might be stretching the edges of the model too much. So JK Tech has been conducting combination circuit surveys on plants around the world for the last 30 years now. So we have established large database with real data of different pieces of equipment performing different duties on a large range of ore hardness as well. That this is a valuable information that we use for benchmarking purposes, including the design of new combination circuits as well. So JKSimMet has actually become a standard tool for the minerals processing industry. There is more than 500 licenses worldwide, where they are mostly used by operations, but also consulting firms, engineering companies, research center, and you can see many references to the JK Tech software, JKSimMet, and the methodology, the drop-right test, or SNC, many references to the methodology or the JK methodology in papers. JKSimMet is a main tool for optimizing and designing combination circuits. So that was a quick review of what we can do with JKSimMet. So I will just go through some of your questions. So I encourage you to start writing your questions if you have any. So I can just take them. So I'll take some of them. Yeah, I haven't. There is one question about the use of the JKSimMet software for HPGR circuits. I can probably show you something about that in a sec. So this is HPGR. Well, this is the HPGR model between JKSimMet. Actually didn't mention it, I think. This is one of the latest addition to the software. has to do with, well, these are the HPGR model. This is one of the latest additions to the software. And it can be used both for optimizing circuits and also for designing circuits. And certainly needs some or characterization that comes from the drop-by test. And then, well, we can go through the model in more detail in training. Okay. So there are, okay, another question talking about fine grinding. So the development, so JK Tech is actually working on the development of the models on a continuous basis. So we are basically keep developing the existing models and working on the addition of other models. So one good example for that is the SAG mill model. I will show you quickly. So I switched that back to the big combination circuit where we have the SAG mill. So this is the current SAG mill model that we use, that we call variable rates model. So it combines operating conditions, equipment dimensions, matching specific model parameters like breakage rates with also breakage functions or specific parameters coming from the SMC or drop-by test, which is the A, B, and TA parameters. So actually, JK Tech is working on the new generation model or new generation version of this model that will hopefully be implemented in the software. So all current clients or customers will have access to the new version, which is now on testing stage. So we are testing it internally. Once that process is completed, it will be released to users in the world. And we will have to adapt our training sessions to that as well. Training. When we sell a license of the software, it includes training by one of our specialists. So that is a 5-day training course. So that's full day. So that's around 40 hours that we can split if that suits the client, which sometimes is not very easy to do because they are in a remote location. So we can go to, say, your operation or to the country you are, and then we do the training. Normally it takes 5 days. It's not software training. Well, it is a software training, but not just a software training. It's actually we go through all the fundamentals on combination, all concepts, so that helps attendees to better understand the models, the combination principles, also the approach of each particular model. And we cover from more characterization, the actual model structures and its limitations. Also, so we run some exercises, and most importantly, if the client during the training have their own survey data available, we can use those during the course. So first you get trained and familiar with the software, and second, at the end of the week, you get your own models developed. So that's a very, very important thing that clients have indicated they liked. Okay. Crushers. So I think this is a good example of crushers. With crushers, actually, Crusher models combine the mathematical models combine the operating conditions like cloud size setting, and also combines the org characteristics, including the SMC or drop by results, like appearance function or energy versus size reduction relationships that we call the energy table, which is this one that you can see here. For example, and this comes from the drop by test. Say these are particle sizes, and these are T10 values, which are indicating size reduction. Say, to get more reduction on this particle size, you need to apply this energy level, basically, in kilowatt hour per ton. And certainly, we can develop models on any combination circuit based on servo data. So in order to get site-specific model for the circuit, it's necessary to conduct a survey, get good quality of data, and then develop the models. Yeah, with the fine grinding, there is, well, in the model at the moment in JKSimMet, there is no fine grinding model as such yet. There is an important fine grinding mill manufacturer that has sponsored the development of a fine grinding model that will hopefully, has been developed already, will hopefully be incorporated in the software quite soon. They are actually completing all these negotiations, copyrights and all of those, and hopefully will be implemented. And there are other models that are being at the moment completed. So hopefully at some point will be also incorporated to the software. Okay, I just wanted to okay, basically that summarizes all the questions. So I'll just want to say so in case you want ask more questions or get our publications on the news, latest news, you can subscribe to JK Tech Today, that is released every quarter with news on the latest activities of both JK Tech and JKMRC, and also the updates of the software, or you have further questions on this presentation or the other presentations coming in the following weeks, please feel free to contact me. So I will be more than happy to reply all your questions. So we are just coming to the end of the presentation. I just wanted to thank you all again for taking the time today to attend and ask your questions, also for your interest in the software. So I will keep in touch with any of you that might be interested in contacting me. Thank you very much. Have a good afternoon.